So root solving, what we're doing pretty much is if you have something like this, and I think I can hold Alt. No, not that one. Control. No, Shift. There you go. So if you hold Shift, you can draw a straight line. If I have something like this, if I have an equation that looks like this, let's assume this is X. Let's assume this is f of X. The whole idea that we have with root seeking methods is that we want to find this point. And I'm gonna draw this. I feel like the guy from Khan Academy. I'm gonna draw this in red because I love red. All right, so that's the point that we're trying to find. We're trying to find the X value that makes such that if I plug in that X value into my X, I get a 0. So I'm looking for that, but X value, kind of like back to college algebra or intermediate algebra. If I take that X and I plug it into my function, I should get a 0. That's the point. That's what we call the root, or what we call the 0. So there are multiple ways for us to do that. And what we're going to see in this class is we're going to look at methods that are able to, if I start somewhere, like let's say I start somewhere in here, this is my initial guess, my X sub 0. And if I plug it into the function, I will get a point right here, which this is going to be the point evaluated at that point, or my function evaluated at that point. That gives me a value that is not a root. Like I want to get to this point, this one down here. So for me to get to that point, I have to start kind of like shifting. I have to apply a root seeking method where I'm going to start doing a bunch of guesses like, oh, X1, X2, and maybe X3 is going to overshoot, and then X4, and then X5, and then it keeps getting closer and closer. And there are two things that I want you, right now I'm going to introduce you to them. I'll probably make a YouTube video about this, but it's a very interesting concept, or it's something that is very important, because we're going to be talking about something called tolerances. If I evaluate an X here, if I have a value here, and this gives me a respected f of X, the distance, this distance, the Y distance, the height. So if I evaluate a function at an X point, I'm going to get a result. That result, that value, the value of that evaluation is what we're going to refer to as the residual. So you're going to see this saying in class, the residual. And the residual, the way that you calculate the residual, it's equal to the absolute value of that function evaluated at whatever X point. In this case, if I wanted to evaluate, if I have an initial guess fx sub 0, and I evaluate the residual at my initial guess, that's a question you're going to have on the exam. What is the residual at the initial guess? You will have that your residual sub 0, so my residual at my initial guess is going to be equal to my function evaluated, the absolute value of my function evaluated at that X. That is what is known as my initial residual. So the residual tells you, and I'll tell you in a second why it's important. The residual tells you the distance. It tells you the Y distance from the function. And this is very important because as we move down this function and we go towards that X, as we go towards the root, what do you see is happening to the distance Y? What's happening? Where is it going? Exactly. So if I can say something like this, I can say if X is a root, if X happens to be a root, X whatever, Xn, if Xn happens to be a root, then this implies that if I were to make the residual at that root, this will be the absolute value of Xn. And what is that going to be equal to? If I approach a root, if I'm at a root, what is going to be the value of my residual? What is going to be my Y value? 0, correct. So that's going to be one of my stopping criteria. When I have a code, my code is going to run forever. My code is going to run forever. It's going to keep finding that root, and I'm going to define something called the tolerance. If I'm going to say something like if the residual at whatever X value is less than, for example, 10 to the negative 3, 10 to the negative 5, 10 to the negative 6, whatever tolerance I feel comfortable with, then I will tell my code to break. Because this, as we saw before, this is the point where my code, like the approximation of the root is going to be like, oh, this is 3, 3.2, 3.22, 3 point, like it starts converging towards a solution. So as the residual gets towards 0, I want to tell my code, hey, once the residual gets close enough to 0, break the code. I don't need it. I'm confident with the solution, because you will see that it's converging to a solution. This is very important because this is one of the stopping parameters that I want to implement in my code. A code, if you don't define a stopping parameters, it will go forever. It will approximate the root Even though it's like approximating the same value over and over, it will go on forever if you never stop it. And so that's why these tolerances are very important, because they're the stopping parameters of our code. And there is another one that I will mention in just a second, but I want to let this one sink in. Like the residual is very important. It's our stopping parameter. You know how to do it. Residual is the absolute value of the evaluation of the function. Why is it the absolute value? Because we care about magnitude. I don't care if it's positive. I don't care if it's negative. I just care about the distance from my x-axis and the value of the function at that x. Like I care about this y distance because I want to see that y distance going to 0. If that y distance is going to 0, then I can trust my approximation of the root. It just makes sense. If you have an understanding of algebra and functions, you know that as you approach that x-axis, the function, the value y, or the function value has to go to 0. So that's, and again, we cannot represent 0 exactly. You cannot say, hey, whenever this is equal to 0, this makes sense in mathematics. It doesn't make sense in computer, because a computer, if it's a real number, it doesn't store it correctly. 0 cannot be represented correctly on the computer, or exactly on the computer. It needs to be approximated. And the way that we approximate it is as 10 to the negative 6 or whatever. Or if you're talking about double precision, 10 to the negative 308. Like that will be like the biggest, the closest approximation of 0 theoretically. Doesn't mean that if you type it on MATLAB, it's gonna work. But that's just for, I thought I was using my damn eraser. God, it's such an awful eraser. What do you mean soft eraser? Give me something that works.
With the drop down lock.
Oh, hard eraser. There you go. That works. Such a weird name. Anyway, but so that's one of the things. Now, another thing that's gonna happen is if I keep approximating this root, like I started at x1, then I move to x2, then I move all the way over here to x3, and then I keep, one thing that you're gonna notice is as the approximation of the roots keeps happening, the approximations, every successive approximation is gonna kind of like dance around. It's gonna dance around that point as it starts merging to the point, as it starts merging to the x value. And this is very important because another thing that can tell me whether my solution is correct or not is something called the iterative convergence. And what this means is, as I keep approaching the root, if my root is right here and I have an x here, and then I have another one here, and then I have another one here, and then another one here, 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 like they just start dancing around that point, the distance between every new x and the previous x should be decreasing as I approach 0, because every consecutive x is trying to get to that point. They're not gonna get farther. They're gonna start approaching and get to the point. So there is something called the iterative convergence, which is represented as an epsilon. And this is gonna be equal to the absolute value of the x n plus 1, so the new one, minus the xn, or the current one. You can think of this as like x2 minus x1 if x1 is one of your iterations. And this tells you a distance. Again, absolute value because we care about magnitude. This tells you the distance between your new x that you just approximated and the previous x. And this is important because I want to see if like, for example, if xn is very close, it's a root, it's very close to the root, then epsilon at that current n, which is going to be like n minus x n minus 1, for example, this should go to 0. The distance between every consecutive x and the previous one has to go to 0 because all my x's are going to start getting closer and closer. Like here's going to be my x1, x5, xc, like x6, I'm sorry. Every single axis is going to get closer and closer to that point. So these two concepts are extremely important, and I highly, highly encourage you to look at definitions, like for residual and iterative convergence. You will see them starting now all the way till the end of the class. We will talk about iterative convergence and residual because they're very, very important. So that's one of the things that I wanted to talk about. So you can write it down, you can watch the recording, and you should be able to see it again. Another thing that I want to talk about is there's going to be 3 methods. And I will talk about this more on the next lab. Right now, I just want to introduce you to the code because I don't want to take too much time because we only have like 40 minutes. But What you need to learn, and this is something that you need to learn how to do it by hand. So I'm gonna write right here, like I'm gonna say learn, and I'm sorry for my cursive handwriting that sometimes doesn't make sense. Learn to do by hand. So you're gonna have to learn how to do these things by hand, and one of them is, or I should write it in a different way. I should say, learn how to do bisection. So learn how to do the bisection method. And the next lab is not mandatory. I'm gonna show the code today. You don't have to attend the next lab if you don't want to. It's gonna be probably me talking about theory and explaining this method. So the first one is the bisection method. The second one is what is known as the Newton-Rapshon method. And then the last one is gonna be called the secant method. And Newton-Rapshon and secant method are very, very similar in the sense that secant method comes from Newton-Rapshon. Newton-Rapshon requires a derivative, requires the evaluation of the derivative. Secant method does not, because it approximated using the idea of the slope and to evaluate the slope. And bisection method requires two initial guesses different than Newton-Rapshon. So all of this information, again, I will go in more detail on the next lab. But fixed point iteration is not lumped into any of these guys. It's more of like the introduction of the idea of root seeking methods. That's iterative fixed point iteration. So it's not necessarily a method. It's more like a method itself, but it's kind of like the stepping stone of everything else. But yeah, these three things, definitely learn them. And from this, also learn, I will say study the concept of residuals, the residual and convergence. And I think I forgot an E in there, but you guys know what I mean. And this one we represented as an R, and this one we represented as an epsilon. So those two things, you're gonna see them in the notes, you're gonna see them in the class notes, and that's one thing that it's very important. But anyway, any questions with regard to this, we can talk about it during office hours, or we can talk about it the following lab. I just think that the earlier you start learning this, it will benefit you in the class, because this is something that you're gonna see on a theoretical side, and it's gonna make absolutely no sense, but it's extremely, extremely easy to do it by hand. It's very, very simple to do it by hand. And once you get into all the theory, a lot of this is lost, just like everything else. You cannot explain mathematics to a non-mathematician unless you make it, you have to boil it down by a lot. So that's one thing that it's very important for all of us to understand, that this class requires a lot of self-learning. You see a lot of theory in the class, it's just thrown at you, and you're just like, man, I took differential equation like 5 years ago or something like that. Yes.
In the notes, like in the lectures, there's also something like fixed point iteration.
Yeah.
Is that like
Fixed point iteration, as I was mentioning before, it's like a stepping stone. It's like it's the idea.
Oh, so all those things are basically fixed point iteration.
They're not. They're separate. Fixed point iteration is a method. Newton-Rapshon is another method. Bisection is another. I can go over the derivation the next lab. And I keep thinking, I forget that you guys are online, but yeah, I will go over the derivation or during office hours. They're all derived from different perspectives. Yeah. So but they all accomplish the same thing. They're all root seeking methods. The difference, and I will go over more detail later on, because they all work in different scenarios. If you try to do a tangent, an inverse tangent, or yeah, if you try to do like a tangent, which is discontinuous, has discontinuities, if you try to use bisection, it will work wonderful. You define your frame, you find the root, beautiful. If you throw Newton-Rapshon at it, it's gonna have a stroke, and it's just gonna oscillate forever. So it's kind of like programming languages. You pick the right tool for the job. But again, I'll talk more about that. So this is the project. This is what the project is gonna look like. And it's gonna be very similar to this, probably not the same problem. We normally alternate between a fluids problem and a dynamics problem every other semester, so it might be different. But again, some of the details can be ignored. I know I receive a lot of emails or people asking me like, hey, I have, for example, the previous one, where do I put problem 4 and 5 on the answer sheet? Just put it on the command window, just put it as an f-print statement. I think the epsilon is this, or I think this. Like you can just put it like that. I'll look at it and I'll just be like, okay, that makes sense. I care more about your familiarity with the code and that you're able to understand results rather than you're answering all the questions. But yeah, so we're gonna write an Octave code to solve nonlinear equations. When they say solve nonlinear equations, it means the point where f of x is equal to 0 or f whatever is equal to 0, whatever independent variable. We're gonna be using the Newton-Rapshon and the secant method. So they both accomplish the same thing. They should both give us the same solution. They're both gonna go at it in different ways. So this application is from fluid mechanics. We're trying to find out the friction factor and determine the pressure and the pressure drop. Now, if you're interested in the derivation of this, by no means ask me. I got an A in fluids. I absolutely, and tremendously despise fluids, thermal, and heat transfer. I hate all of those three classes. I'm a vibrations guy. I'm a controls guy. I like electrical stuff. I like computers. I do not like fluids. But you're more than welcome to ask me and I'll go over this derivation. I'm just saying that you're not going to get the most passionate response from me. But yeah, there's nothing wrong with them. I just don't particularly like them. I worked for Siemens before. I'm tired of turbines. Okay, so according to extensive experiments, Colebrook arrived to the following expression. This is the function that we will be defining. We will define this function, and we're going to use it. F in this case is the independent variable, as you see from the input. F is going to be the independent variable. R is the ratio of the surfaces that's going to be given, and RE is the Reynolds number that's going to be given. So this two, everything that you see in here that you don't know what it is going to be given. Those are constants, and they will be provided to you. This will be the function that you're trying to find the point where the F factor is equal to 0, and that will give you your friction. That will give you your corresponding friction factor. You don't need this for anything. You are gonna use this function once you find your F, once you find the F, the friction factor, like from the output of your code. Once you find the friction factor, you're gonna use that friction factor to calculate the head loss. And you use this equation. D is the diameter, L is the length of the pipe, V squared is the velocity, and G is the gravity. And everything is in English units because why not? But yeah, you're gonna calculate the head loss. This is not included in the project, but this is a very, 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 very easy question. If you understand functions and you know how to bring output out of the functions, because the function that I'm gonna show you brings no output. But in the next lab, I will show you how to, in more detail, how to bring output from a function. But if you can figure that out, you pretty much have the whole project because you're given all of the values, so you're given all of the constant, and then it says, use the Newton-Rapshon method to solve this using an initial guess of 0.001. And you can defend it using symbolic manipulator. Yeah, don't use any of this. You can determine the derivative. So I think you're given the derivative. I don't know if they're gonna give it to you this semester, but here it is. Like I think last semester somebody started like complaining about it because they didn't know how to do basic derivatives. And so this is the derivative. So this you have to type it yourself on the code. I think I already have it, but otherwise you will have to type this. And it's a very, you see the ddx of log e of log u is just a substitution. But yeah, you're gonna pretty much evaluate it using that f and find the answers from that f in phi. And the reason we're giving it here is because again, we require an initial guess. If you read about Newton-Rapshon and you read about secant method and bisection, all those methods require an initial guess. If you don't have an initial guess, you have to give it an initial guess in order to start. But yeah, that's going to be the project. The project is just going to be evaluation of the friction factor, use it to calculate the head loss, and then create like plots of the convergence and residual. Well, yeah, make sure you go to the project and read it whenever it's posted. When is this project going to be posted? I have absolutely no idea. When is the answer sheet going to be posted? I have absolutely no idea. The only thing I know is that we will have a quiz whenever the project is due. That's all I know. But anyway, all right. So let's start with the code. And I will have, Do you guys have any questions before I continue? Anybody in the chat? No? Okay. All right. So this code is going to be slightly different in the way that, as you can see from the right, I have three files. I have what is known as a main file. I have a Newton-Rapshon function file, and I have a secant method function file. So there are two things that you can do. In MATLAB or Octave or whatever you're using, if you have a main code, if you have a main script, you can always, let's say I start this and I go CLC, close all, whatever I always do. I'm gonna call this temp. I can always define a function like this, like function, and then I can say the output, and then I can say this function, I'm gonna call it add two numbers. This one is gonna take an X and a Y as an input. And what this function is gonna do is it's gonna say result equals to X plus Y, or I'm gonna call it addition. Addition is gonna be equal to X plus Y. And the only reason I'm talking about this is because I want you guys to understand. So if I create anything in MATLAB, any result or anything inside of a function, if I want to bring this output out of the function, if I want to bring it out because I want that to be the output of this function, I have to write it here. I have to write it here in between brackets. Why brackets? Because MATLAB understands matrices, it understands arrays. I have to bring that scalar out as a function. And here's my main function. So I can, if for those of you more familiar with C, I can think of this as my main function. And then I can say display, I can say, for example, define X as 2 and define Y as 3. So if I call my function and I'm gonna say result is equal to add two numbers, and I'm gonna pass that X and that Y as my inputs. So that's gonna be my result, and then I can say display my result, right? So what this is gonna do is it's gonna start from here. It's not gonna necessarily start from the function. However, it's a good practice that you always put your functions at the beginning of whenever they're called. So if I'm calling the function here, something that you might hear, for example, from Python, Python doesn't care where you define your functions. Like you can call a function at the beginning and it will look for it and then it will use it. MATLAB and Octave do the same, but they're not as reliable. Like you can define your functions at the bottom and it will work like one time and then the next day it won't work at all. So definitely be careful of that. I always like to define my functions before I call them. So that's one of the things. And this is one of the results. And so when I run this, I should get, let me minimize this. I should get, in my command window, I should get 7. So why am I getting 7? Because 5 plus 2, this 5 is being passed here. This 2 is being passed here to this function. So it's going to take X and Y, and it's going to return addition. So this is the basics of functions. Let's say I want to multiply these two values, but I don't want to create a whole function to multiply. I want to bring out another output. Then I will say here, I will say multiply is going to be equals times X times Y. And I also want to return this. So what I'm going to do is instead of in C where you do return, multiply, and you can only return one thing at a time, instead of doing that, I'm just going to write it up here, separated by a comma, and I'm going to say multiply, right? What this is going to do is this is going to create an array. It's going to create an array that has two cells. It has the result from the addition and then comma the result of the multiplication. That's what this is going to do. So if I want to call this guy's result, I have to say this is result addition, for example, and then this is result multiplication, something like that. And then that's gonna bring the two results from calling that function. It's gonna put them in there. And so I can say result addition if I only want the result from my addition, which should be 7. And then if I want the result from my multiplication, then whenever I do it, it should give me the result from the 2 times 5. So outputs are handled in MATLAB in the sense of matrices and the sense of arrays. because if you remember from algebra, if you remember from number of functions, you can only bring one output out of the function. But if that output happens to be an array, you can bring whatever is inside of the array, because technically you're only bringing out one thing. So I want you to look at this. I want you to get the main idea, because again, your functions are supposed to bring output. But if you look at your functions, I wrote them so that they don't bring anything out. They do whatever they have to do, and they don't bring anything out as an output. But yeah. Now, this is also important because I want you to look at this. This function, I have it combined with my code. My code and my function are the same script. I can do the same with main, Newton-Rapshon, and Secant. I can combine all of them as one script. Like I can take Secant and I can copy this all the way down, and I can paste it in my main code all the way here, like at the top. I can paste it here, and it will work fine. It will not be a problem. However, something that is a good coding practice is something that is called modularity. That means if you have a big project in mind, if you have a big idea in mind, you separate your functions. If your functions are long, you separate them. Look at secant function. This is a somewhat long of a function. If I put it in the main script, I have to scroll all the way down to whatever line 200 or something, line 300 or something. It's just easier to separate things so you know exactly what's not working. Maybe your Newton-Rapshon is working, maybe your secant is the one that is not working. So it's easier to know which one is not working by separating them and be like, okay, I'm just gonna use Newton-Rapshon. I'm not gonna use secant. I'm gonna like put a comment whenever, like if I look into my main code here, at this point here, I call secant. Let's say there is something wrong with my secant, I can just comment it out, and that's it. And then I'm not calling secant because I write my function in a way that all the outputs, print statements, and everything come from the function itself. They don't come from the main code. Yeah.
Would you want to reference a function that's in another file, I guess?
Yes.
How do you do that?
That's exactly what I'm doing here. Do you see that here I'm calling Newton-Rapshon? Yeah. And what is the name of the function? Newton-Rapshon. So that's one thing I was getting to that point. Thank you for asking. This function, if I were to take this function and let's say I want to create a new file, and that file is just going to have that function. Let's say instead of having it here, I want that function to be here. And I want to call it with the same name, add two numbers, and that's going to call this function called add two numbers. What you have to keep in mind, and this is extremely, extremely important, most of the errors come from here. If you define a file to be just a function, nothing else, just a function, when you save that file, the name of the file has to be the same as the name of the function. So if the function name is add two numbers, the name of the file has to be add two numbers, exactly the same. If it's different, it will not find that function. You have to they have to be exactly the same, yes.
You call multiple functions in one other file and then call those multiple functions.
I have never tried that. I will say it like that. I think it's possible. I have never done it myself. Usually when I create a file as a function, it's because I have a big function that does one thing. I have never created files that have multiple functions. I have done it in C, but that's usually when you do like include something.h, like it's a library. Yeah. I think that has a bunch of functions. It's called a library.
So it doesn't work like this isn't like library.
This is not like it could be. It's out of my understanding. That's what I'm trying to say. I have never had a reason to do something like that. I'm sure there is a way of doing it. I don't think MATLAB is a good programming language, but it's not a programming language in a sense. It's a platform for numerical calculation. So a lot of the things that are like object-oriented, MATLAB has object-oriented. It's a sorry excuse of object-oriented. Like you don't create classes and things like that in MATLAB per se. So certain things that are very common in coding are not in MATLAB because it's not the objective of the platform. But very good question. Will we need another display to show both, or can we? You can use another one. I'm sure you can separate them by a comma, display, and show both of them, but it will not show them nicely. Usually, if it's values like this, I like to use an fprintf statement. So there are no header files. I'm not sure. Look into it and let me know next class, or let me know during office hours. I will probably have an answer in office hours, or because I'll look at it today or tomorrow. But yeah, so that's the reason I have a function called secant which the name of the function is again the name of the function, or the name of the file is the name of the function, and Newton-Rapshon, where the name of the function is the same as the name of the file. Now, if you work with people from a different lab, a lab that doesn't belong to my lab, they will have a different code. Why is this? Is it because I'm trying to get in trouble? No, it's because I think the code's stupid. I think that if you're doing certain things, you have to do them in a way that they make sense and not in a way that they make the code more cumbersome. And that's something that I want you to take. If you don't take anything out of this class, and I don't think I'm looking at the comments, if you don't take anything out of this class, at least what I want you to take out is, hey, how can I be a better programmer than what everybody else? Okay, so again, this is the function. This one, I'm gonna start by declaring none. This is the project 2, root finding method of nonlinear. I always start, this is not an optional thing. Always write CLC clear and close all, because we want to clear our command window, clear our workspace, so we're not dragging old values into your new calculations, and close all because we want to close all the graphs. You don't want to sit there and click X, 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 X in like 20 graphs, which at the end of this class, we have like 10 graphs, but I'll show you how to combine all of them. But that's why we use close all, so we start fresh, we start from the beginning. We're gonna define the project values. Again, R is the friction factor, and not the friction factor, I'll tell you in a second, is the ratio of the surface roughness. So all of this is given in the project. I have my R, I have my Reynolds number, and then I define my functions. Once again, we define them as inline functions. Towards the end of the semester, or if you're working on a different lab, they may not define them as inline functions. They may define them as a file, as a whole file that says, hey, this function, it's called, it brings like an output. It brings y, and the function is called f, and it takes x. And then they literally write f of x equals 2 times something something, and that's it. So you're wasting a whole file to be a function. Instead, again, why is important? You define them as inline functions, because inline functions don't get stored in the memory. The only reason we use them is to find a value, save that value as a vector, and that's it. What is the space in line 20? This is the built-in, I'll get to that in a second, but this is the built-in Octave root finder. There is a routine that is built in within Octave, and we will use it to compare results, because this is supposed to find the root, but that's exactly what we're trying to do. So I will define my function. This one is my function. This one is my first derivative. Instead of using f, I'm using x. You can use f. You can use m if it's a dynamic problem where you're looking for the mass. I use x just because it's more intuitive. I know I'm looking for a root. Commonly, in whatever equation, x is the root. So I'm just going to call it x. I define the tolerance. Again, if you are working with someone from a different lab, they will have two tolerances. Most likely, or usually, the tolerance that is defined, and this is what I was talking about before. This is the residual of my iterative convergence. In most labs, like in the other sections or in most projects, you are gonna be given a tolerance, and it's gonna be the same for both. Like it's gonna be like residual is 10 to the negative 3, and then iterative convergence is equal to residual. Like that's always what they're gonna do. So you're creating two variables for nothing. I rather just call it tolerance, and that's a tolerance for both of them. I define my initial guesses. Again, why do I have two of them? Because Newton-Rapshon requires one initial guess, but secant method requires two initial guesses. You have to give it 2 points because secant method, as the name implies, create a secant line. This, you don't have to worry about this. The only reason I have this is to compare results. Octave has a function called F0, not the GameCube or the Nintendo 64 game, but the root finder. It's gonna find the zeros of a function. And I can pass in the function, and I can pass the bracket of x values where I wanted to look for the function. So again, not important until the end. The only reason I have this like this is because I wanted to be able to plot it, and which is the same reason why I have dots. Again, the only reason I have dots is because x is gonna be passed as a vector for me to plot it before I start doing my calculation. So if you don't want to plot it, you don't have to plot it. The only reason I plot it is because I like to do this. It's gonna take a while, but I like to be very visual as much as I can, and that's the point that we're looking for. So the red line symbolizes y equals 0. So that's the 0 axis, and that black dot that you see, that's the x value that I'm looking for. I'm looking for an x value that gives me that point. So what x value, which I can kind of like eyeball that it's going to be 0.01 something, but I want the exact value of x, which when I plug it into the function, the blue function gives me 0. So that's the whole idea of the root. That's the whole reason why I have all of this plotting. You don't need it if you don't want to include it. But then this is something that you're gonna see that is quite different from the other labs. And I am calling the functions. Like I say, hey, give me the result of Newton-Rapshon, pass the function, pass the derivative, pass the first initial guess, and the tolerances. That's all I need. If I do it on paper or if I do it on the computer, that's what I need. I need my function, the first derivative of my function, an initial guess, and my tolerance. I need the tolerance on the computer to tell it when to stop. You don't need it if you're doing it on paper, because on the exam, we will tell you how many iterations to go. But the same idea with secant method. So this is why it's very good to have functions, because instead of saying, okay, I'm gonna calculate Newton-Rapshon and I'm gonna write everything and then I get my result and then I'm gonna write the whole definition of secant method and then I'm gonna write, no, because let's say I had different functions. I had an F2 as well. I could take this thing and I could call Newton-Rapshon twice and I could pass two functions. Like assuming I wanna use the second but the same tolerance. Like I assume F2 and dF2 are two different functions from the previous one. I just have to call that function again, and I will get my result. Now, you might be asking, what is the output of this? The output of this, if I were to run this, and I will show you in a second, you see that there are more figures. There is this figure, which belongs to Newton. This is supposed to say secant, by the way. I forgot to change the title, so I'll do it in a second. But I get two pictures, but those figures are nowhere to be found on this code, nor this output. So where are they? It's because I define it so that when you call the function, let's look at Newton-Rapshon. So this is called Newton-Rapshon. Let's look at the function Newton-Rapshon. So this is the function Newton-Rapshon. First of all, I want you to notice that there are no outputs. If you are going to be outputting something like an array of values, like I have the array of values here. I think it's called x. If you want to bring out that vector of values of all the roots, or if you wanna bring out the whole vector, you type x here. That will tell you all of the roots, like starting from the initial guess all the way to the most accurate approximation. If you're just calculating the head loss, if you're not calculating anything else, just the head loss, you want the last one, because the last one is going to be the most accurate. So you put x equals n. So now x is going to calculate x, it's going to be the most accurate approximation, because it's going to be the x on the last iteration. But if you change this, make sure that you give it a name here. You can say x result or x Newton equals to that. It's still going to do the same, but now it's going to save that x into x Newton, because again, you need that root for the project. So I'm going to leave it there. But yeah, xn will be the output. Newton-Rapshon is the name of the function. This takes an f, a df, an initial guess. It doesn't care which initial guess is, because again, if you don't understand why I'm calling it here, these are all temporary names. They all get replaced. If you're rusty in programming with C or anything like that, see me during office hours and we'll go over that. I'll try not to focus too much on the coding, and I have like 10 minutes, I think, or 5 minutes. But anyway, this is the whole process of the Newton-Rapshon. We define our initial guess, and or convergence or residual, define the number of iterations. So all of this function, and I will just go through it. All of this function does the calculation of the Newton-Rapshon. This one is the function of the Newton-Rapshon. I do an infinite loop. If you look at different labs, they're going to be doing different things. Some of them are going to do for loop. Some of the project is going to also define something, the max number of iteration, which is going to be 1,000. I don't use it. It's redundant. There's no reason to. Because I am setting some if statements. If my residual and my tolerances at the current iteration are less than the tolerance, we're good. That means my code convergent. My residual and my convergence, they both went to 0, which is exactly what I wanted. I explained what residual was, and I explained what convergence was. So if they're both going to 0, we're good. If they're both getting huge, or either one of them is getting huge, that means my code is not convergent. I am going to break my code. So I don't need a for loop. I can just put an infinite while loop because one means true. I can just put an infinite while loop and go through that. But anyway, just go through the code, and this is the code. And let me show you before. You guys can leave if you have to go somewhere. That's fine. But I want to show you because I want to keep it on the recording, the secant function. So this one is going to be the secant function. Again, there is no return. I'm going to add it so you guys can use it for the head loss. And I'm going to go back to main and add it here. I'm going to say x secant. It's going to be equal to that call of the function. So that output gets called, and you can use that for your head loss calculation. Initial guess 1, initial guess 2, function and tolerance. Note this one doesn't require the df. Here are my initial guesses. Here are my iterative convergence, my residual. I define a counter. It's 2 in this case because I start at the second iteration. I'm going to have my print of the header. Again, infinite while loop. Calculation of the function, calculation of the iterative convergence. Looks that is exactly what I show you on the drawing tablet. The current x minus the previous one. Residual absolute value of that function. Yes?
What is percent %E?
Where? Oh, it's to write it in scientific notation.
Okay.
Yeah, so percentage F writes it in decimal or in real format, and then E writes it in scientific notation. So this is all printing. Don't worry about this, it's all printing. This is important again, 2 if statements. If my residual and iterative convergence are converging, I break the code. If they're getting too big, I break the code, yes.
Should we use fprintf instead of printf?
Well, I don't think you can you use printf? That's only for C.
That's what I was using.
That's where and it was working?
It was just printing in the command window.
Okay, yeah. I mean, if it works, it works. I know MATLAB doesn't allow you to do it. Octave is different. Octave is made by a bunch of people who are programmers, so they do whatever they want. But yeah, and this just brings out, and you can see that my plots and my output of my functions are in my function itself. So that's why I don't do any printing on this one. But anyway, if you have any questions with regards to this, just let me know, send me a message. And how does it know to make additional plot? Because I'm calling multiple figures or multiple subplots. I can explain the subplot later during office hours or something. But yeah, if you have any questions, just look at the recording. I'm gonna go through it one more time just to make sure that it's there. But if any questions, just let me know. I'm gonna slowly go through it. The Newton-Rapshon. I'm gonna start from here. And then the secant method. And that should be everything. So let me minimize this.